everyone. Welcome to Isaac. He's going to be doing a talk a little bit about, it looks like an industry talk about using Crystal and some lower level features and in his business. I've chatted with Isaac off and on a few times, and he seems to be one of the people who has been using Crystal kind of the longest in the industry setting. I know there are some people that have done it longer, but he's the one that I've known that's done it the longest. If you're ready, Isaac, we can hand it off to you. Are you ready to start presenting?
I should be fine. Yeah. Okay. Well, greetings from Phoenix, where it's a pleasant 42 Celsius, 108 Fahrenheit. So my name is Isaac Sloan, and I'm Ellerist everywhere on the internet, pretty much. So anywhere that there's a communication channel, you can probably find me as that. I've been developing software professionally for a bit more than 18 years now. Some of my passions are obviously my family, and then Ruby, Vim, Crystal, C++, C, open source, coffee, not CoffeeScript. And you can see this picture of, some latte art I've been working on. And so let's move on. So I apologize in advance for the Crystal pun, but I just kind of couldn't help it. I mean, it kind of makes sense. I think Crystal makes the code a little bit more readable, hence, crystal clear and, the language. So I'm going to be talking today on binary messaging, specifically moving on to binary messaging in CAN, which, all vehicles, I would say, yeah, probably all vehicles except for, pedal bicycles are communicating in CAN bus at this point. Which is actually a very old protocol. I mean, similar to MIDI for those of you involved in like music. But it still holds its own fairly well. Obviously, bandwidth is limited, so bit packing is extremely important. So moving on. So just really high level, you're probably aware of from anyone who's taken a networking class or, is aware of how just high level communication works. There's multiple transport protocols. That's actually what sends the messages once the messages are packed from one place to another. Well, I mean, technically that's a network protocol, but the transport protocol is what packages it up and has, the logic for verifying that it was actually received correctly. In the case of like TCP/IP, in the case of UDP, it just sends it out and receives it, but doesn't actually bother verifying that the correct thing was received. There's multiple other ones. In some cases, like CAN, transport protocol and network protocol, and all those are kind of rolled together, and there isn't really a huge distinction between them. And what I'm going to be talking about is actually decoding the messages, decoding the bodies, rather than really the hardware, network layer there. And yeah, I mean, there's quite a few of these. I see I had CAN twice on that list, so I guess, good thing it's about that. So from a message encoding perspective, you're probably familiar. On the right side, I have like XML, JSON, YAML, SOAP, and I mean, quite a few others that, messages are encoded in. If you're looking at, anything in the modern open source or even closed source web world, you're probably familiar with, sending messages back and forth in JSON. 15 years ago, it was XML or SOAP. Messages can be sent in YAML. Usually they're just stored in YAML though. On the upper right circle, I have some binary ones such as message pack. There's actually a pretty good library in Crystal for message pack. Message pack is very similar to JSON in that it has key values, but it's efficiently storing the values, which is useful. Because you're actually sending the key along with every message though, it's still not very efficient. BSON is used in Mongo and is also a communication standard somewhat similar to JSON, but binary. Protobuf is Google's, which is more used, not necessarily with key values, but you have software or code generated on both sides that say this is how you would decode that. For instance, like, these bits are going to be this, these bits are going to be this, etc. It's very reliant on their libraries, and it's sort of hard to create a new library to the standard, as everything's, well, you see that languages don't adopt that nearly as fast just because of kind of the somewhat closed nature of the standard, even though it's technically open. Then you have packed structs, which are really low level, and I'll get to that in a second, which is essentially taking a struct, taking all the values in the struct and just returning byte for byte how that is, and then loading it back into the struct when you get it to decode it, which is similar in a way to protobuf, but like lower level. And then bitfields. So here we go. So C structs, you're probably familiar with these from college or past programming career, maybe current. So you have a struct. In this case, I just call it telemetry data. Inside of that struct, I have multiple integer values. In most processors, that would be, an int would be a 4-byte value or 32-bit value, similar to an int in Crystal. However, some compilers and for some processors are going to be only 2. I'm assuming 4 though, so that's where I have this uses 20 bytes of memory. Going over here, this is actually using a bitfield, hence a bitfield telemetry data. Have the exact same values in here, but I've defined that this one temperature only takes, oh, my bad. This one temperature only takes 7 bits. Active only takes 1, so it's either true or false. Identifier is 8 bits, so anywhere from 0 to 255. And then fault is, and it takes 4 bits, so anywhere 0 to 15. And then same as critical fault, 0 to 15. So in this case, it's all able to easily fit into 4 bytes. Technically, you could fit a lot more values into 4 bytes as well, but obviously it's still limited by byte boundaries. So we've taken this from 20 bytes down to 4 bytes. At this point, you could take the packed value of this and you could send it across a network and then load those bytes into this struct and have a struct that represents all the values that had been sent. This is a fairly efficient way of messaging. However, I mean, Crystal doesn't natively support C bindings currently against a bitfield C structs. But there are a lot of, kind of easy ways and quite a few libraries, one I wrote and a couple others I've seen in the community that do a decent job of decoding bitfields. Moving on to, let's just move on. So one problem with using bitfields or packed structs is, well, you have to choose an Endianness, right? So you're either big Endian or little Endian, and all the values are going to be interpreted that way. And I mean, that's great. Unfortunately, a lot of communication, especially legacy communication in the industry, is using combinations of little Endian and big Endian, such as bodies of information or CAN data that exists that have mostly little Endian or mostly big Endian with some of the alternative in the middle. That would be obviously impossible to decode with a bitfield. Let's talk a little bit about Endianness. So in the case of little Endian, bytes read out more or less as you'd expect. If you were talking about an 16-byte value, then that would literally be this byte here, byte 0, and this byte 1, read in order, which would, make a lot of sense in terms of human translation and in terms of even just coding against it. So, I mean, all you'd really have to do is just grab those bits and translate the value of that. In the case of big Endian, if you were to do the same thing, you would have to take like byte 0 here, which still runs the same way. So, I mean, the order of what they call the words, the bits in the word are still running the same direction. So for instance, like all ones in this byte would still be 255. But then in order to combine that, you would have to take this byte and essentially stack it on the other side of this byte if you were to try to just like, human translate that. So if you were to have a 16-bit value, you would have to look at this byte first and then switch over. So in this case, the 8th bit, or if you're starting at 0, so the first bit of the second byte would actually be here, which means you have to pretty much read everything like this, and then this, and then this. Moving on. So this is CAN syntax. Let me try to move my face out of the way a bit. Okay, so this is the way CAN syntax works for a CAN message. So higher level, CAN is sending across, as you'd expect any network, with these are headers, and the headers are telling it this is what the CAN frame is. that would be, there's also the message ID right here. So the syntax of the actual can frame body would be, well, essentially this. So you would have the body. This is the DBC right here. A DBC is a type of file that represents how to decode a CAN bus. So in the DBC, we're saying expect message ID 158. It's going to be called vehicle example status. That's not going to be contained, obviously, in the frame. So we have to know that here. The size of it is going to be 8 bytes. So it's not, so that's important to know, because then you know how much of the body to read. And then the sender in this case is going to be, BCU. Let's just say that that's like, body control unit or something. So then this right here is a signal, which is, the definition syntax for signal. So every message, in this case 158, could contain, as many signals as can fit into that 8-byte body. So we have the signal, we have vehicle example, message 1. In this case, M1 is an optional multiplex bit, which essentially means that you could have the exact same bit fields contain values for multiple things. Maybe like left mirror, right mirror, for instance. And so then if the capital M value is 1, then it means, left mirror. If it's 2, then it would mean right mirror, or, you could do that all the way down. Let's not really talk a lot about multiplex bits though, because we don't have a lot of time. So the important part here is a starting bit. So in this case, we're saying starting at bit 0, and then the length in bits is going to be 4. So that's 4 bits. And then the Endian this is going to, in this case, be little. Remember how I said before that messages within the body could be either big Endian or little Endian. So in this case, this is little, which is great. And then the plus means that it's signed or unsigned. Plus means unsigned because, it's a positive value. So, and then you have a multiplier, which is also a thing you couldn't really have with a, with a bit field or just a pack struct without additional code. So you have the multiplier, which is saying multiply the value by 1, which means essentially no change, and then subtract 0, which again, no change. In this case, we're saying the minimum value here is going to be 0, and the maximum value to expect is 8. Typically, that should line up with the maximum that could be stored here, i.e. 16, but that isn't actually always the case. In this case, we're saying that the unit is going to be, in this case, I just, threw this in for like, a tuple, but really, or an enum, but really it could be like, percentage, it could be Fahrenheit, Celsius, whatever. In this case, the sender is just like, I don't know, I can't remember what I made up UCU to be. All of this is, fake data, obviously. If you want, we're interested in any DBCs for like any vehicles you're currently driving. That's pretty much all available on GitHub and pretty easy to get from like, people that have figured out how to decode that on Raspberry Pis and stuff. So feel free to take that for a spin with this code. Okay, so here is an example from a DBC file, like the full example that we were just looking at. You'll see I have message 1 through 20 here and the starting bits, and how long they go, as well as all those other pieces I discussed. Down here, I've actually taken this little Endian 64 bit or 8-byte byte array, and kind of broken out these little pieces. So you can see with the first one, message 1, 0 through 4 right here, message 2, 8 through, 5 through 8, or if you're starting at 0, then like, 0 through 3 and 4 through 7. The interesting thing is when you get to this one, notice this is 9, and this is because of a big Endian value. So if we look at 9 right here, well, you'll notice that it actually starts at 9, but it goes 10, but it's using 10 bits. So, 2 bits more than the 8 bytes, the 8 bits in a byte. So in this case, we're actually starting at 9, which is right here. And it's so it's using these values, but then because this byte actually stacks because of big Endian, then we end up with these 2 bits right here ending up over here after 9. So when you're showing this within, little Endian, everything 1, 2, 3, 4, 5, 6, 7, 8 makes sense, but then 9 wraps back to there. So that's kind of a, a caveat with like obviously using big Endian and little Endian together. You have to be aware of that. So moving on, here's another example of the same thing, which is generated within vector's DBC editor, which is like a free program that you can use to visualize and edit DBCs. It's not very user friendly, but and I couldn't figure out how to change font size, so I apologize for if you can't read that. But you'll see the same thing with that big Endian value right here, a vehicle example message 9, where this is the least significant bit starting here on the 3rd byte. And then you have the most significant bits actually on the first 2 bits of byte 2. Now moving on to programming. Most of you are probably familiar with bitwise operators. If not, here's a quick review. So we have bitwise, and pretty much is combining 1 and 1. If they're both 1, then you end up with 1. So I mean, across the entire bytes, and every 0 and 1 in it would be combined, and you'd end up with the value there. Or is doing something similar where it's saying if 1 or the other is 1, then it's 1. XOR is saying if 1 and 0 or 0 and 1, then it's 1. If it's 0 and 0 or 1 and 1, then it's 0. Left shift is similar in a way to multiplying by 2. You're shifting everything to the left 1 space, which means a 1 becomes a 2 becomes a 4, etc. One obvious caveat there is if you already have, like, say, 8 bits and you shift them all the way to the left, you're going to lose the most significant bit, which is going to change your value. And if you shift back to the right, you're never going to get that back. In the case of right shifting, you're actually throwing the least significant bit off to the right. So, you're losing that. But in the case that you only care about a specific section of bits, this is very useful. Bitwise, one complement is pretty much just flipping every bit to every 1 to 0 and every 0 to 1. It's similar to 2's complement, which is how you do a negative number, but I guess we don't have time for that. Moving on. So here's some crystal code. So in order to decode little Endian, we're taking in a starting point and we're taking in a size. And in this case, because it's little Endian, it's pretty easy. We're just saying that the shift is the start value. And then we are taking the CAN body, which is in this case is a 64, UINT 64, since pretty much every CAN body is no more than 8 bytes. And we're shifting it the distance over that the start is, because we don't care about any bits outside of there. We're then creating a new value for 1 of whatever type T is, in this case, UINT 64. And we're shifting it over by the size, so 16 bits, and we are subtracting 1. This is creating a mask, which is going to zero out all values, which essentially we don't care about, because we only care about getting this value that starts at 0 and goes 16 bits. We're then converting that number to bytes, and we're using IO byte format little Endian decode to turn it back into whatever value we pass in here. In the case of decoding big Endian, this is a little bit more difficult. What we're actually doing here, getting the shift value is a little bit more difficult as well. So I have this build shift right here, which is taking in the start and the size. I'm using div mod on that to take whatever the start value is and get the dividend and the modulus. And then figuring out, okay, starting at whatever the size of it is, in this case, 64 again, or I guess 8 in this case, multiply it by 8 to get the 64, subtract it by the divisor times 8, minus 7 minus m, subtract by size is giving me the shift value here. At that point, now that I have the shift value, I'm flipping this to little Endian. Well, in this case, I mean, the entire body is little Endian anyway. So I have my little Endian bytes. I'm then using those bytes to convert the entire thing to big Endian so that I can still look at it in a format that, makes sense. So essentially, I'm ending up with bytes that are stacked as little Endian, even though the value is big Endian, but I flipped them so that they're easier to work with. In this case, I'm then taking the can body, I'm doing the same thing, I'm shifting it over, and yeah, shifting the entire thing and adding the mask. And then in this case, I'm getting the bytes again, and I'm converting it back to little Endian. So this one's a little bit more difficult. All of this code I'll publish on GitHub, so you can look through it in more detail if you want. So here's how we inject a value back in. So in the case of little Endian, value getting put back into the can body. So we just showed how to get it. In this case, let's say we take this same value, it starts at 0, it has a size of 16. So we get that value. The value is going to again be size t, which in this case is uint64. So any other value passing into this will be converted by Crystal to uint64 as long as it's possible to do so. In this case, I'm taking the shift value again. I'm creating a mask, which I'm then shifting over. And a mask again is just ones over just the location that I care about. So everything else will be zeroed. I'm then taking the value and I'm shifting it to its correct location within the, because say for instance, 1 is just going to be, the first bit is going to be 1. So I'm shifting that over to where it needs to be. In this case, starting at 0, I'm not actually shifting it. I'm now taking n and I'm applying the mask to it. This gets rid of any possible values that exist in it accidentally that could cause an issue and overflow into like another value. For instance, somebody passed too big of a value in or something. In this case, I'm now taking the full can body, I'm masking it with a complement to zero out the place that I'm going to overlay my value. And then I'm ORing the value onto that section within the bits where the zeros would be. Injecting big Endian is obviously more difficult. I'm using the build shift value again to get the shift value. I'm getting my bytes. I'm switching it to big Endian, which again is stacking the bytes in a way that makes more sense, so I don't have to like jump back and forth a lot. And then I'm creating the mask and shifting it over to the correct location. And then I'm taking, I'm shifting the value over to a correct location, masking it to make sure it doesn't overflow. And then I'm taking the ones complement of that mask, masking the can body, which again is the little Endian can body that we've converted above. And then we're taking the shifted value and we're ORing it into there. And then we're flipping it back to the correct order by taking these big Endian bytes and decoding them using big Endian, which again is just flipping the bytes, and then turning it back into a uint64, which is how it's stored. So yeah, now the last thing we really need is a readable DSL. And fortunately, Crystal macros come to the rescue there. I apologize that some of these fonts might be a little small. I couldn't really make it any smaller and still fit it on the, or larger and still fit it on the page. But here we're taking the can field. I'm saying this is the name, this is the start, this is the size, this is a multiplex. If it has one, multiplier, offset, Endian, signed, min 0, max 255, etc. This allows me to pass in a uint64 value or 8 bytes. There's multiple initializers. And then I can print out the values. I can, I can print out, so I could print out all the bytes. I could print out whatever all the values are. I could set the values, and I could, again, print them out to see that they have changed. And yeah, let me quickly switch over and share my terminal. I think that is the thing I could do. Maybe desktop 1, terminal, that looks good. Okay, so hopefully you can see my terminal. This is all the files within this simple library. Let me just run that example I showed above. So that would be Crystal Spec. Actually, let me open it up really quick. I know I'm almost out of time. So if we look at this file right here, test script, you see I'm loading in the fake data here, and then I'm printing it out, and I'm seeing that it changed. So let me just end that. So see Crystal spec. Sorry, it's in the spec folder. Okay, so you see in this case, these are the bytes in little Endian, these are the bytes in big Endian. Here's the values. Then I go and change the values and print them out again. And you see that this value has changed to 500 and the 2 has changed to a 3. And then you also see that the bytes have also changed because of that. Okay, so last slide, which is, here's this GitHub can example. And you can reach me basically everywhere as Ellerist.
Thank you so much. Thank you,
Thank you.
Isaac. Thanks for the talk. See you around.
Have a great day.